In the previous segment, we discussed about motion in 3D, that is the curve on which the particle seems to be moving. It is in 3D space, but we used two very specialized coordinate system. One is cylindrical, one is spherical. And now in this segment, what we are going to do is we will extend the NT coordinate system which we had discussed for 2D, that is for a movement on a plane, okay, curvilinear motion in 2D, that we will extend to 3D, okay. And we will see that see these cylindrical and spherical coordinate which we discussed for 3D, they are suitable for many applications, but this NT coordinate system is useful when the path is known a priori. For example, the same example which I had given in 2D case, suppose the map is flat, then the 2D will do, but then suppose we are moving on hilly area where the map is not anymore 2D, it is having a third dimension also, then can we estimate everything like the acceleration of a vehicle moving on that, which is changing its speed in some very arbitrary way, continuous function. So, in such cases the NT coordinate system will be very useful. It will be much clearer once we start discussing and then see that. Okay. Now, to give the foundation on which our discussion will happen, it's like this. Suppose we have a 3D space, and on that 3D space, suppose we have a curve something like that. So, it is a 3D curve in this 3D space, and we are trying to see, say, the position vector, suppose here. Our particle is at such a point, say P, and let us assume that it is moving say in this direction, okay, on the path with some speed, whatever it is. And now if you remember from that previous segment, we said that its velocity is v e t, right, and we said that in this direction e t is suppose the unit vector and v is its speed. So that was our direction of et, and then in 2D we just said that the radius of curvature we said and drew, and then in that direction we took the en vector. But now things are much more complex, so we have to see in detail, okay. Now for that there are two changes. If you have noticed the title of this segment, it has also been mentioned path variable, okay. Now what that is, it is nothing but this v, if we write in terms of ds over dt, okay. Now we are talking about this, that is a path variable. That means the distance which we have covered. For example, suppose there is a curve and we pick any point as, say, starting point. That curve could be even continuing from this point, but any point we choose on that curve and we call that the starting point. And suppose we measure s, that is the arc length along this path, okay. S is the arc length, and then that we use as a variable, not time, but that arc length s as a variable. So then it is called a path variable, and we will see how beneficial it is to represent everything. For example, here we had written r, isn't it? Now till now we have been using always r as t, but now in this section we will use r as a function of s. Now time is a scalar variable. Similarly, s also can be a scalar variable. It is just a different parameterization of that same curve. Earlier it was the parameter was time, and now it is the arc length. So that is the only difference. Okay. But by doing that, we will see that a lot of algebraic simplification happens. Okay. So it is a mathematical convenience for which we are we tend to use this r as a function of s. And that s here, if we take ds over dt, is nothing but the speed. So that is how in the definition of velocity it comes into picture, the path variable. So that is one part. Now the other thing is, in 2D it was very easy to define the radius of curvature, but in 3D it is slightly tricky. The point is, if we take say another point on the curve, maybe here, okay, after some time and some distance, say here it is r t prime or r s prime, okay. So whatever, some other time and some other distance, and at that point let us say its movement is in this direction. So that means our et is in this direction, right. So at that particular instant of time. Now if we try to draw these vectors et and et at t prime and et at t. Now if we try to draw them tail to tail, which we did in the case of 2D planar motion, now it may not be possible. It may so happen that this line and this line may not even be crossing each other, because these are two vectors in 3D, and so there is no guarantee that they will even touch each other. Okay. Now that is why here everything is, you have to be very careful in defining things. Okay. Now how do we define then the radius of curvature, which has to be defined, because if we move ahead we will come to a point where we will require that. Okay. So that is the thing which now, that means, see here why did we use or put those two vectors tail to tail, because we wanted to see the change what is happening within a certain time. Now here also we will require that, and that is why or where we will face the trouble. Let us see where we will need it. Suppose the velocity we have taken like this, the acceleration will be calculated by taking the derivative of this velocity vector. Now that will bring us to say what? 1 will be d square s over dt square times et. That part is one part, but then the other thing is ds over dt times et. Okay, I will write maybe okay et dot. Now this is the thing which now we are quite acquainted with these things. Here there is no problem, this is a unit vector, but this is not yet a unit vector. It is the differentiation of a unit vector with respect to time. So basically now our job is to evaluate d et over dt. Okay. Now how to do that is the question. Now as soon as we require this to be evaluated, we know that we have to draw them tail to tail so that the difference can be measured. And here the problem comes in 3D that they may not even intersect. So, how to do that is you bring this point as close as possible so that we will reach a point very close, okay, here somewhere, so that we can approximately say that these two vectors now will intersect each other. Okay, so that means ET here and ET at say here ET at t plus delta t. Now we bring them as close as possible so that they will now start intersecting each other, and at that distance or that situation, as soon as they start intersect each other, that can define a plane, right? Two vectors crossing each other. So, there is a common point and there are two lines. So, that will define a plane, and that plane, if I have to draw, maybe I will draw, okay, something like that. So, it will be maybe something like this. Okay. So, let this be the plane on which or which contains both this ET at t plus delta t and ET at t. Okay. Not now this with this vector I wouldn't have been able to define this plane. Now once I come close enough, then at some point when they are close enough, they will have an intersection, and that intersection will define this plane, and then on that plane I can now draw the perpendiculars to these two vectors. So, on this plane, okay. So, let me draw with white only so that you will understand that one perpendicular to this, the other perpendicular to this. So, this point will define my center of or center of curvature in a way at that, and this plane its name is oscillating plane. Okay. So, oscillating plane. Okay. The word oscillating means kissing. So, in a way this plane is just touching or kissing the curve at that particular location, okay, at which the point is presently positioned. So, and our radius of curvature is defined on that oscillating plane. And now we can draw say ET like that, say ET is this and this is ET at t plus delta t, and so we are drawing these things on now the oscillating plane, okay. And now then this portion will give me the delta ET, and suppose this angle is say delta phi something. Now earlier in the case of 2D, that was very easily related to the center of curvature. Okay. Now how do we correlate this, evaluate delta ET? So that's the question. Okay. Let's see. Now coming to this, it's again the same thing. Its length is unity, so that means its magnitude magnitude of delta Et is nothing but delta phi, because this length is of unit length. Okay. Now, if that is delta phi, what is the direction of that? The direction can be seen to be, or even this magnitude, let us calculate. See, this length is say delta s. Let me show that as, so this one, let me use a different color. So this part, okay, so this part is, you know, it's delta s. Now over r, so this if I write this as say r, fine, it's quite becoming complicated, right? So delta phi is nothing but, because this angle is delta phi, is nothing but delta s over r, this r being the radius of curvature, which is defined on the oscillating plane. Okay. And now what is the direction of this? It is in the direction of perpendicular to this, so that means En. Okay. So that means this we will define as, say, this is nothing but limit of delta Et over delta t when delta t tends to 0, right. Now this part, let us say I will move it a bit here, maybe. Let us say the delta s has come, but let me try to take that separately. Will I be able to? I think, yeah, good, great, yeah. So fine. Now what to do with this? Here its magnitude is delta s over r. So delta s over r, okay, I have to take the limit, right? So limit, this is delta s over r by delta t anyways, and then its direction is in the direction of En, because this has to be perpendicular to En. So its En also is existing on the oscillating plane. Okay. So that means in the limit you get to be it's that's it, that's fine. Now here we will do a simple algebraic manipulation, that det over dt is nothing but det over ds times ds over dt. Now this is nothing but the velocity or the speed, and this can be calculated as, so now instead of dt I can simply yeah, so best thing is I can change it here, okay, that's fine. Now this will become, shall I go to the next page or something, or let me try to do this. So this delta s will be cancelled out, and okay, let me take it here. So det over, so here basically I am writing delta s, okay, I'll do that. Okay, I'll make it say delta, sorry, I'll make it, it's easy here, delta s times, I will shift it here and I will write delta S by delta T. Is that fine? Okay. Now this delta S cancels out with this, and this is my speed, and 1 over r. So delta Et over delta T is nothing but your speed over r times En. Okay, that's it. Now, so this we wanted to basically replace it here, right? So that is what we were about to calculate. So now I can go to the next page where I will write the acceleration was, how was it? D square S by dt square. So this is nothing but d square S by dt square and Et plus ds by dt times what did we get here? This much is there, and in place of that we get V over Ren. So V is nothing but again ds by dt En. So now you see we are in terms of unit vectors. So that means we can write here that this is nothing but d square S over dt square Et plus I missed 1 over r, right? See here, this 1 over r I missed. So into, so 1 over r. So this plus ds over dt square over r En. Okay, so this is the expression for acceleration in terms of the path variable. And to exactly tell one thing, okay, there are two things which I want to just point out now. One is see this. How do we, so now you think about this. These things are just from the speedometer you are getting. This is the direct speedometer reading, and this you are differentiating the speedometer reading one more time. But now how to calculate Et and En is again the question, which at that time in 2D it was easy. Here to calculate that, let's say Et, it is nothing but you remember we said that everything we will express in terms of S. Now if you do that, this will be nothing but dr over ds. Why so? Because you see here, suppose you have a coordinate system, then there is a path, something like that, and then think about a point like that which is r of s, and then another point which is r at s plus delta s. Then think about this vector which is the difference, so delta r. Okay. Now as we make delta s tending to 0, this vector will become tangent, okay, and you see that this length, I'll make it say blue. Now this is delta s and this is delta r. So once we go to the limit when delta s tends to 0, these two lengths will become identical in that limit. So that's why if I take delta r by delta s in the limit that delta s tends to 0, I will get, in fact, dr over ds, which is nothing but Et. Okay. So that's the way to calculate ET. It's easier if you replace or if you express R as a function of the path variable. Okay. In fact, and then we had this expression, right? Here you see this. Now En, how to calculate? From there you can say that now En, sorry, I'll write in this color again. So now En you can write by observing that see here, from here I can actually write 1 by Ren is so here det over ds, because V I can divide and that ds by dt if I multiply. So I can, this is nothing but det by ds, which is nothing but this. Okay. Now this expression will allow me to write this as R times det, sorry, I don't like this, det over ds. Now again see, this R is a function of S, so it's easy to differentiate to get Et, and again you are just differentiating that. Now this also will be a function of S, you are differentiating that again with respect to S and multiplying with R to get En. Okay. So then it boils down to find out R. If you can find out R, then everything is figured out. Okay. En, Et, R, everything. Now how to find out R? If you remember the formula for in 2D, it's you know it's you remember this formula, right? Dy by dx whole square to the power 3 by 2 by d square y by dx square. So that's the formula which generally we use to find out the radius of curvature in 2D. But in 3D, if you really want to find out if it is not in terms of the path coordinate, it will become, I'll just show you this expression. I'll just write it without any proof. For proof you can consult any maths book. So that will become, say, R will be, say, R prime dotted with R prime to the power 3 by 2 divided by R prime and dotted with R prime times R double prime dotted with R double prime minus R prime dotted with R double prime. It's squared, and this is the thing. Now in 3D, if R is not parameterized in terms of the arc length, this is how you have to evaluate. For example, this prime is the differentiation with respect to time. Suppose R is with respect to time, then you have to do this. But if R is expressed in terms of time, then when small r, the position vector is expressed in terms of S, that is the arc length, then R will be nothing but 1 over means I'll say d square R S over d S squared, its magnitude. Okay. Because Et is nothing but dr over ds, and curvature is nothing but the change in the tangent vector, means rate of change of tangent vector with s. So its magnitude inverse is nothing but the radius of curvature. So this is the simplicity with which you can calculate R if a position vector is defined in terms of s, and then that you can use to see. That means in summary, now you see everything in going back to where you had started, that you have a path. So that means and then for which you have the knowledge of position vector in terms of arc length. So that is the most important part, that is in terms of path variable you have expressed the position vector of the particle, and then you have the speedometer reading. So these are the two things which you have at your hand, and now you see how with that you can calculate everything. So this is from speedometer, this is differentiating the speedometer data, and then you have r as a function of s. This you have from the map in terms of path length. So differentiate it with respect to s, you will get it, and then you differentiate again that with s, you will get this term. Now to figure out r, you do this, that is dr, again you differentiate with s and take the mod, you get r, and substitute here, you get n, and all the terms are known. So for such difficult problems where the path could be a very complex path in 3D, this is the most natural way to find out the acceleration vector. Okay. So this is very important. It will be much clearer once we solve many problems related to this, and we will see them in the next segment. So see you in the next segment.